Okay, good afternoon, everyone, and welcome to this special Abdus Salam Memorial Lecture that we hold at ICTS. This is a lecture to honor Professor Abdus Salam, a giant of theoretical physics from the Indian subcontinent, and who in addition to his impact in physics, also played a very important role, as you will hear today, in creating the ICTP, which has played again a very important role in Indian and other countries as well in the development of not only physics, mathematics, biology, many areas. Here at ICTS, we have had these lectures for the last decade or so, and the theme is often sort of to weave in both academics as well as the larger impact of the science we do in policy, in public affairs, in the world at large. And we've had a number of excellent speakers in this, including Professor Vijay Raghavan, the former PSA, the Professor Fernando Quevedo, who was the predecessor of Atish at ICTP, and Professor Kasturi Rangan, who had passed away, many other luminaries, Professor C.N.R. Rao, in fact, also. So it's been a lecture series which has its special identity, and I'm delighted today that this year, being the centenary of Abdus Salam, it's particularly fitting that we have none other than the current director of the ICTP, Professor Atish Dabholkar, here to give the Abdus Salam Memorial Lecture. And so I'll very briefly introduce Atish to you, but I think many of you know him. Atish is a brilliant theoretical physicist and who has made very significant contributions to string theory, black holes, holography, and also connected many interesting new areas in mathematics to physics and vice versa, such as modular forms, etc. So Atish was actually a senior of mine, though we didn't overlap in IIT Kanpur. He was, by the time I joined, he had actually graduated, but in the same 5-year MSc program at IIT Kanpur, and after which he went to Princeton and did his PhD with Jeff Harvey, one of the senior-most leaders in string theory. And after stints at Harvard, Rutgers, and then a long-term position at Caltech, he returned to TIFR in Mumbai, where he was part of in the late 90s, early 2000s, the vibrant string theory group there. And so he was, while there, many of his important works got recognition, such as through the 2006 Bhatnagar Prize, the Fellowship of the Indian Academy of Sciences, and so on. He moved then to France, and where he was at with the CNRS as he had the chair, the excellence of the CNRS, I would say, in 2007. And then he moved to ICTP, where, among other things, he was the head of the high energy cosmology and astrophysics section, and then took over, I think, about 6 years ago, I think, as the director of the ICTP. So I think I won't keep you waiting any longer. Let me invite Atish to come and tell us about unifying nature and unifying the world, something which desperately need at least the unifying the world part.
Okay, so I should start. So thank you, Rajesh. It's a particular pleasure for me to be, to be giving the Abdus Salam Memorial Lectures at ICTS in the centennial year of Abdus Salam. So this was just a coincidence. And also, I'm very happy to be here at ICTS and to see with my good friends who are here, many of them who I have been close colleagues with, to see that ICTS has also come up in a wonderful way as a younger sister of ICTP, you could say, in somewhat similar model of an international center to bring in the best people together. So it's my pleasure to be here. So thank you for the invitation. So I thought that it would be really appropriate for this kind of occasion to, in fact, because these are also the two themes that are close to my heart, unification of forces in the sense of unification of all fundamental interactions, and the impact that an institution like ICTP has in unifying the world, in particularly increasingly fractured world. And ICTP has had this role also in the past, and perhaps it's even more so, it's going to be more important in the coming years. So I'm going to crisscross between these two themes. First, I will talk about unification of forces, sort of building up from the beginning to up to where I have been working on. And similarly, uniting the world, starting with ICTP's original mission to how we envision it for the next 60 years. We just celebrated our 60th anniversary last year, 2 years ago. Doesn't work. Okay. So, so I was told that this will be a broad audience, so I will keep it. So one of the most famous examples of unification is electricity and magnetism. So this is electricity, a very different phenomena than magnetism, which is a very different phenomena. They are drastically different, apparently nothing to do with each other, but they turn out to be the two sides of the same coin. So the idea is that unification is that diverse manifestations of a single whole, two very different. So this is basically, even though they look very different, they're joined together at a deeper level, and that's the meaning of unification. So this is what would you say is electromagnetic unification. So you have an electric charge, but if the electric charge is in motion, it becomes electric current. And electric charge, by Coulomb's law, produces electric field, whereas an electric current, using Ampere's law, creates magnetic field. So there is a reason to believe that there is something, and of course now we understand with special relativity, the two things are really very, very closely connected. You cannot distinguish them. So magnetism is basically electricity in motion. And this was the famous discovery of Maxwell. And he wrote down these very simple equations. dF is equal to 0 and d star f is equal to star j. So j is like the current and f is the electromagnetic field. So these are some second order differential equations. And this led to yet another unification of electromagnetism and light. So these are really three sides of the same coin. So this is electricity, this is magnetism, and with Maxwell's equation, there is a wave-like solution where the magnetic field is oscillating that way, electric field is oscillating that way, and the wave is propagating in some direction, and that looks like light. And this is, if you pause to think about it, it's a spectacular discovery. You didn't put it in, and light comes out of Maxwell's equation. And not just light, X-rays, radio waves, the entire electromagnetic spectrum suddenly got compressed and unified into a single whole. So this is perhaps by far the most spectacular and most influential unification one can imagine. But there have been subsequent very important, theoretically very important and perhaps more complex unifications, which are what I want to talk about. But before we go there, so far I have talked about the electromagnetic field as a classical field, but it was understood in the early beginning of the last century that photon is the quantum of light, and the classical electrodynamics is just an approximation when you have large number of photons present. Otherwise, the particle nature becomes important, and that led to discoveries like laser. So things like laser and so on are also now incorporated in this unification. And this is one of the most spectacularly successful theories of nature, that these are some electron magnetic moment. Theory agrees with experiments to so many digits. So it's something remarkable, which of course all of you must have heard before. I'm just reminding you. Now we go to Rutherford. Now Rutherford did this famous experiment, and actually has seen it in CERN. It's a simple experiment. He just bombarded a gold foil with alpha rays coming out of, and he was expecting that, because the conception of atom was like, it's a kind of a fuzzy object with total charge negative, zero. So since the electrons have negative charge, somehow it is like filled up. And he said that he was shocked that it was, there was something really hard sitting inside. And most of the time the alpha rays would pass through, but once in a while they would bounce back. And this led to this notion of an nucleus. And there are two more forces were uncovered in the process. So far we are with electricity, magnetism is one force that we have unified. But now you had a strong nuclear force which holds the nucleus together. And then there was a weak nuclear force which was discovered with radioactivity, because of which the nucleus decays. And Rutherford not only discovered the nucleus, but he really set in motion this whole method of doing physics, which is what we do even today. It's at CERN, basically we smash things together and we try to learn what is inside. It's like smashing two cars and looking at what comes out. It's a steering wheel comes out, then you learn that there is a steering wheel. And so we now understand, as we know in school physics, that a nucleus itself is made up of protons and neutrons. And inside that there is quarks and so on. So now, starting with this simple experiment of Rutherford, we have gone into this gigantic, several kilometer long Large Hadron Collider, and an amazing detectors of this kind. You can see a human being standing there to detect what comes out of these collisions. Now, that raises a question: what principles govern these new forces? So Maxwell had these very nice equations. And this looked like a total mystery. And one of the pioneers of quantum electrodynamics, really one of the founders, Freeman Dyson, had this to say: the correct theory will not be found for the next 100 years. Okay, he was not very optimistic about it. This was in 1960. And it is sometimes shows you that eminent scientists can be eminently wrong. And the gauge principle, the unifying principle, turned out to be the gauge principle, what you might describe as SUN quantum gauge theories. So it's just a generalization of quantum electrodynamics. In some ways, a very simple-minded generalization, a somewhat obvious generalization. What is remarkable is that it actually describes nature. So this I would call unification of principle, because why would you think a priori that strong nuclear force is described by the same kind of mathematics as the weak nuclear force, and a similar kind of mathematics as the electromagnetic interactions? But sort of just playing with it, physicists figured out, Yang and Mills and various people, that a relatively simple generalization of quantum electrodynamics, at least at the classical level, it's a relatively simple generalization. At the quantum level, it turns out to be very subtle and complicated, which took several decades to understand properly. But at the classical level, the generalization is simple. So this was Maxwell's electromagnetic field. So there is electric and magnetic field is all sitting together inside the symbol F. And you had one charge, one type of charge, electric charge. It can be +1, -1, +2, -2, but there is only one kind of charge. Now, it's natural to ask, what if you have two kinds of charges? Then it turns out that the electromagnetic field has to be a 2x2 matrix. And you have two kinds of charges, up charge and a down charge. Or you can have three charges and a 3x3 matrix. You can have a red, blue, and green charges. And surprisingly, this basically exhausts. Basically, electromagnetic force, this is U1. U1 is a bit different mathematically, but okay, roughly speaking, is the same series, U1, SU2, SU3, and you can imagine you can do SUN by N matrices. So this is electrodynamics, this is weak nuclear, and this is strong nuclear. Roughly speaking, actually, I will tell you now more precisely. So now that raises the question, can you go and unify this further? And this was the question that Salam asked, and to which, apparently when he presented this to Pauli, so he asked the question, could the weak nuclear force be joined together with the electromagnetic force? And then Wolfgang Pauli, one of the founders of quantum mechanics, is supposed to have said, let no man join together what God hath torn asunder. This is like a joke on what you say when people get married, that let no man tear asunder what God hath joined together. But it turned out that Pauli was more clever than wise. And he was again eminently wrong, another eminent physicist. And in fact, it turns out that electroweak unification is indeed possible. And this was one of the, again, a very major discovery of the 19th century physics. It had some new ingredients like spontaneous symmetry breaking, new particles like the massive vector bosons or the Higgs boson, which I've heard about. And that's what led to the Nobel Prize of 1979 for Glashow, Salam, and Weinberg. So now we have unified electricity, magnetism, and weak nuclear force. So let's continue. The search continues, but now I will switch I'm going to switch the theme shortly. But one analogy to think about unification is like, this is a beautiful temple of electromagnetism. And here you worship the deity of electromagnetism. And here is another beautiful temple where you worship the deity of weak nuclear force. And then one day you discover that there is actually a secret passageway when you do some digging, which connects the two temples. And actually they are part of the same temple complex. And henceforth you worship only one deity and not two deities. So this is a kind of an analogy of what unification is. And this has led to the standard model of particle physics, which you must have seen in popular descriptions. But it's quite remarkable that with just a few quarks and few leptons and few particles which carry force, you can pretty much describe everything from your phone to your iPhone to your lasers and everything that nuclear energy, and including the Higgs boson. So now, so I hope if there are any questions at this point, I'm happy to answer. Now I will switch to the other theme. So this is the beautiful location. This is ICTP on the Adriatic Sea near this nature reserve, which is also a heritage. It's a protected bioreserve area. And now I would like to talk about joining forces to unite the world. So ICTP was founded in 1964 thanks to the efforts of Salam. And very importantly, his partner was Budinich, who is sometimes less credited. but who played a very critical role, an Italian physicist. Because you have to remember, and I was actually quite impressed with Salam when I read about it, that he thought about it not when he had a Nobel Prize. I mean, he was very generally highly regarded scientist, but he didn't have like a Nobel Prize to go up to Italian politicians and ask for money. So he was really driven by this idea. He was probably less than just turning 40, that he wanted to have an international hub for science. And it took many twists and turns. It didn't happen. I think this was presented first to the International Atomic Energy Agency. Robert Oppenheimer was the first chair of our scientific council, who was tasked to give direction to this new effort by the Atomic Energy Agency. And there was in 1996, I think, after Salam passed away, the tripartite agreement was signed between the Italian government, International Atomic Energy, and UNESCO. And since then, we are governed by this tripartite agreement. So it's a very unique UN organization. We are a UN organization. We are all UN employees, where two major UN organizations are collaborating with a member state. And the idea of ICTP is really to overcome the barriers of gender, ethnicity, but also more importantly, as we all understand in India, geography and economics. And ICTP has played a very important role on the world stage in achieving this. So just to give you a very quick idea, something like more than 200,000 scientists from basically every nation in the world has visited ICTP over the years. 67% are from developing countries, what used to be developing countries, and I will come to this point later. About 30% are women, and they are all fully funded by ICTP to attend 60 very high-level conferences and also for long-term collaborations. So roughly we get every year about 6,000 visitors. And this has helped to build scientific communities around the world, including in India. I mean, I was myself, when I was at Tata Institute, I myself, even though Tata Institute, like ICTS, is very well funded and with very nice facilities, there was something nice about going to ICTP to have the opportunity. And many of my colleagues here who have been closely, also when we organized the Strings Conference, ICTP came forward with substantial funding. So ICTP has been kind of a guiding, let's say, lighthouse, as I will say. And it has contributed to many important breakthroughs, including to some Nobel Prizes, but also other very important breakthroughs. So the idea is really like an international hub for science. It has a unique mission that excellence at the frontiers of science, global inclusion, and international cooperation through science. That was roughly how I would state the vision of Salam. And I think he has this very nice quote in his Nobel lectures that scientific thought and its creation is the common heritage and creation. Sorry, I have repeated, but scientific thought is the common heritage and creation of all humankind. Of course, Salam wrote mankind, but I'm changing it to humankind. And this ICTP's impact, just to tell you now, this ICTP was celebrated very nicely, the 60th anniversary. This is at the United Nations. I was very happy to have the opportunity to present to the member states the impact of ICTP. And on one of the high-level meetings, actually. And what I want to emphasize is that we had 3 people whom we invited to give testimonials. So one of them is Raji. He came from a small village in Ethiopia, from a modest family with 4 children. And it was evident when he went to university that he was a brilliant student. And so his professor told him that if you want to do physics, you have to go to ICTP. So he was always dreaming of coming to ICTP. He came to our master's program. He actually did a very nice project with me, actually. It turned out that he worked with me. And then he went to MIT to do it. Now he's doing his PhD at MIT. And so he spoke about how sort of without ICTP, he would not have had the opportunities. This is Estelle. She is from Cameroon. She did her PhD, and also then she was associated with ICTP, and now she was at Perimeter as a and now she has gone and she's become an entrepreneur. So she's founding her own company. This is Minister Rapapa. He is the Minister of Science in Lesotho. Lesotho is this small country in the middle of South Africa, landlocked country. And he was a student at ICTP. So it sort of gives you an idea. So this was a very nice presentation at the United Nations. It was like a proof by with the pudding. So ICTP has this kind of an impact also around the globe. We have supported not only activities at our Trieste Center, but all over the world. And you can see it has had a huge impact. In India, something like 12,000 Indian scientists have been to ICTP, including myself and many times, many of my colleagues. I'm actually now working on some agreements with DST and MOS and some institutes. So I'm actually hoping that we will strengthen this collaboration even more. Major conferences like Strength 2001 or workshops on quantum information to neutrino physics organized in India have been funded by ICTP. So I believe that it has its impact on internationalization of Indian science. It helps to internationalize and nurturing the research environment in India. And as I will explain, my sort of looking to the future, the vision for ICTP is really we should think of equal partnerships and not, I will come to that towards the end. Now let's go back to the first theme of unification, unifying nature. So of course, the most obvious omission in my presentation was gravity. And that's the first major force discovered with a 300-year-long history, or several hundred years long history. And Newton's law of gravitation predicts planetary motion in great detail. So the question is, how does gravity fit into the scheme of things? And as we will see, I mean, it turns out that this business with the gauge principle really doesn't work for gravity. Gravity is a completely different kind of beast. So question becomes, can the force of gravity be unified with other forces? But even before we do that, there is another unification was necessary, which is the unification of space and time, having to do with the relativity of time. And it follows from the fact that moving clocks run slower. So if you're in a train, your clock runs slower. Now, how is this possible? Actually, it's very easy to visualize if you accept that the speed of light is constant in all frames, which is actually an observational fact, then you can make a clock by an oscillating light ray, two mirrors. A light ray goes up and comes down, and that you say is 1 unit of time. So you can, this is a nice video. Suppose you have two clocks set to 0, and they are just bouncing light like that. But this clock sets in motion. So you can see that the light in the second clock has to travel much longer distance. And just by Pythagoras' theorem, by a simple calculation, Einstein was able to derive the Lorentz transformation in one line, once he understood how to define time properly. So if this clock shows 5, this clock shows 4. And physically, it's easy to understand. If the speed of light is constant, and if it has to travel more distance, then it's going to run slower. Of course, the funny thing is that the speed of light is constant, but that's a fact of nature. So this led to, you could no longer think of a space interval and time interval as separate things. The time interval, space interval is getting transformed into each other. So this is what I would call unification of space and time. And speed of light is the universal speed limit. This is 1 trillion meters per hour. It's not, like few kilometers. Nothing can travel faster than the speed of light. And this has two dramatic consequences, which will actually play a role in what I have to say next. One is gravity waves, and the other is black holes. So why does this universal speed limit lead to the concept of a gravitational wave and the concept of a black hole? Okay, again, you can sort of understand it heuristically. There is a very fundamental logical inconsistency between this universal speed limit and Newton's law of gravitation, which you learnt in school. What does Newton's law of gravitation say? The force of gravity between the sun and earth is the mass of the sun times mass of the earth divided by the square of the distance times some constant. Now the question is, suppose the sun were to disappear suddenly, when will we come to know about it on earth? If you are a Newtonian, you would say that instantaneously, because if you put one of the masses to 0, it would have to be instantaneous. But we have a universal speed limit. So this really was a deep puzzle for Einstein, because basically gravity was not consistent with special theory of relativity. And that led to his famous struggle to unify the two things to create the general theory of relativity. Otherwise, only in general relativity, the two things can live together harmoniously. So this led to another unification of gravity and space-time. And the unification is that instead of having a flat space, you just have curved space, and that looks like gravity. So there is no force of gravity, it's just curvature of space-time. And it's easy to understand, for example, in a Euclidean surface. Suppose there are two people here walking to the north, following their nose to the north, parallel to each other. Suddenly they will discover that they meet with each other in the North Pole. And they would say that, oh, maybe there was a mysterious force of attraction between the two of us. But there is no mysterious force of attraction. It's just that they were living in a curved manifold. If you do the same thing with time, space and time, then basically you get gravity. So gravity is the force of attraction, which is just a fictitious, in a way, fictitious force of attraction. It just happens because you're living in a curved space-time. So this led to a more generalized notion of relativity of time and generalization of Newton's law of gravitation, and that predicts gravitational waves, because now nothing can travel faster than the speed of light. So if the sun were to disappear, it will take 8 minutes for the signal to reach us. And by the way, this actually bothered Newton. If you read Newton, Newton was among the first to realize how ludicrous was his theory. He says that no competent person in the possession of his faculties can imagine that if I wave my hand, the moon will come to know about it immediately, right? I mean, it really bothered him that there was instantaneous action at a distance, and he didn't have a good resolution. He was criticized for it, but he very wisely, it was like a tactical decision in his research program, that it made sense to make that assumption, even though he did not have a full understanding of it. And it took, of course, 300 years before we actually, or even more, to actually find the detection of gravitational waves. And as you know, here are also colleagues who are working on LIGO experiment. Now let's come to black holes. So black holes, again, is heuristically easy to understand. You know that if you throw a stone, it falls over there. If you throw it faster, it falls further. If you throw it really fast, it will start going around like a satellite. Or if you shoot it upwards, it will escape. And so that's the escape velocity. But imagine if the escape velocity, so a rocket can escape gravity roughly around about 1 kilometer per second. That's the speed of a rocket, a little less. But speed of light is 300,000 kilometers per second. Imagine you make a very humongous Earth, very small radius. Like if you compress the entire sun solar mass into 3-kilometer radius, then basically the escape velocity is equal to the speed of light. And then again, you're led to this logical inconsistency. If what happens? Because light cannot escape this. And once again, when this famous Schwarzschild solution was found, Einstein actually wrote a wrong paper arguing that how the Schwarzschild singularity, he called it a singularity, it's actually just the event horizon, cannot exist in a theory of reality or something like that. And he was not, he was completely wrong about it. And it really bothered a lot of people. Eddington, for example, famously tore down Chandrasekhar for his work on Chandrasekhar limit, which again showed that if the sun runs out of nuclear fuel and it's sufficiently large, it will just collapse gravitationally. So black hole is a very natural consequence of the universal speed limit and the unification of space-time and gravity. And this will play an important role. So now this is a sort of artist rendering of a black hole. It's called black hole because literally it is supposed to be whole in space-time. Like here, I could be passing through a black hole and I wouldn't know. I could be crossing a horizon. I mean, so there is a more mathematical way of characterizing a black hole. I mean, one simple way is to say that the escape velocity is as much as the speed of light. That's a kind of a heuristic way of saying it. But another more precise way of saying it is that it has this stationary null surface. I mean, so it's a surface which is both stationary, it's not moving with, it's not changing in time, but at the same time it is moving at the speed of light. It doesn't make sense if I tell you like that. But one of its properties is that it's a one-way surface. That means it's like you can come to my lecture, even if you get bored, you cannot go out. If the black hole horizon was there, you would be able to come inside but not leave this room. You can fall in, but you cannot get out. And this was, again, resisted. This concept was resisted for 50, 60 years. I mean, sometimes we take it for granted, and we overlook the intellectual struggles that have gone into making even simple things like the coordinate transformation from Schwarzschild geometry to the crisscross geometry. I mean, it took decades and maybe another 50 years for people to accept its reality. And now, of course, there is the spectacular evidence. This is a kind of a reconstruction of two black holes merging into each other, and their final mass is much smaller. So all the rest of the mass is exploded in gravitational waves, an enormous amount of energy, but all in gravitational waves, not in light. And we detected it. This was traveling for 1 billion years, and we detected it recently, like in 2016, when was it? 15. So this is the rendering by the LIGO people. And the little dots are stars. So they are moving around because the space-time geometry is getting. And then it settles into a final black hole. So that leads us to the final frontier, which is the quantum gravity. That how do we unify this force of gravity with the remaining forces? Now, unification has been a very inspiring guiding principle. Electroweak unification was an important milestone of my predecessor at ICTP. And for the 21st century, for my generation, this remains one of the exciting problems to address. And there has been quite impressive progress at a theoretical level, not yet at the experimental level, in making these two paradigms come together. The main point is that gravitons behave very differently from photons. So just the photon was the quantum of electromagnetic wave. Graviton is the quantum of the gravitational wave. And it has a very different properties. But you expect that those properties become relevant at the characteristic length scale, which is the Planck's length scale, which is trillion times smaller than the nucleus. So you might imagine it's a hopeless task. Maybe we can never make progress on a problem like this. And this is where string theory comes in. String theory was kind of was discovered accidentally, but it turns out that now in the subsequent years, one has discovered quite rich connections also with gauge theories, which I will come to. So something that one absolutely did not anticipate. But originally it was actually conceived as a theory of strong interactions to describe the strong nuclear force. It turned out to be a wrong theory of that. Then it was thought to be a theory of gravity, which is, I think we still believe that is a theory of gravity. But then a surprising connection was discovered between the theory of gravity and the theory of strong interactions, which I will come to later. So electrons and photons look like that, described by the gauge principle, gauge theory. And they are like the two electrons, photon, electrons go around. And gravitons look like that. And they behave very differently, as I told you. I won't be able to explain why. But this quantity actually is divergent, whereas this quantity is finite. So somehow gravity was not fitting in the normal framework of quantum field theory. But in string theory, both these things look the same, because both a graviton and a photon are different oscillations of the same string. So different notes of the same violin string, different notes correspond to different particles. And since this diagram is smooth and it has no this edgy points, it's not a graph, but it's really like a manifold. It is free of all the divergences that occur in quantum field theory. So it's really a finite theory. And this property is quite spectacular. I mean, in quantum field theory, you're used to dealing with divergences. In string theory, because you replace graphs with smooth manifolds, there are no divergences. And that is actually one of the reasons that convinced many people in the beginning that there is something. So it's a little bit like you have one kind of Legos, another kind of Legos, mechanos, and string theory somehow figured out the screws that connect the two things. Now, how do we make progress? Because we don't have experimental guidance in this case. So we are in a peculiar historical situation compared to, let's say, when the weak or strong nuclear force, there was really plenty of data. Data was not a problem. Theory was the problem. As Dyson said, the theory won't be discovered for another 100 years. We are in the opposite situation. The theory is kind of reigning supreme. But it looks like the experiment will take another 100 years before we can really verify our theory. So how do we even be sure that you are not misled and you are not fantasizing? I think one very important tool which has been very solid guide is, I mean, if you follow some very robust principles of physics like thermodynamics, entropy, quantum mechanics, principles that you believe in, and if some consequences come out of it, then you're forced to believe in them. And that is a kind of a time-tested way to make progress, even when you're not able to directly connect it to experiment. And that's what we were able to do, starting with, of course, very path-breaking work of Hawking, in which he discovered that putting quantum mechanics in the presence of a black hole, he discovered that black hole actually is not black. It is like a hot piece of coal. And anything which is hot has like some degrees of freedom that are oscillating. Like here in this room, the room is hot because there are atoms going around. And the number of ways the atoms can organize themselves is called the entropy. What Hawking discovered was that the surface of a black hole, so black hole is hot, but moreover, the surface of a black hole is like a hologram. The degrees of freedom that describe what is going inside a black hole are like the ones and zeros. The qubits are stuck at the horizon of the black hole and not inside the black hole. This is very counterintuitive if you think about it, right? To describe the physics in this room, I would really need to, if I put some lattice, I would need a qubit at every lattice site and not at every lattice site on the walls of this auditorium. But that's exactly what the Hawking's discovery showed. And then the horizon of a black hole, not only is it like a hologram, but it is in fact described, I'm simplifying a little bit, by this famous gauge theory that we had encountered. So Hawking's discovery connected and subsequent work on holography by people in my generation like Maldacena and Klebanov, Witten, and Polyakov, people discovered that the horizon is like a hologram and it is described by a gauge theory. So this is sort of coming a full circle. You started it's a unification of ideas, if you like. You had an idea of gauge theories, and you had idea of general relativity described by Riemannian manifolds, all these things. And somehow the two things are somewhere related. That the horizon of a black hole contains information about a gauge theory and vice versa. So gauge theory is equal to string theory. But this is again a very shocking thing, that string theory came by itself, gauge theory came from some other sources, and it looks like there is a deep connection between the two. And now how do we make the connection? Okay, can we test this gauge theory versus? And this brings us to Ramanujan, and this is kind of related to my own work, so I will be very brief. So Ramanujan was interested, one of his famous work together with Hardy was to answer this following question. How many ways can you partition an integer? So let's call that P of n. So if you take and using different colors, you could use two colors, for example, here. So 3, you can write it as 1 plus 1 plus 1 in so many different ways. So P of 3 is 10. Now the question is, what is P of 200? Or what is P of 250? And what if you had 24 colors or different number of colors? So this is from the movie of Ramanujan.
Same numbers. 3,438,532,321. That's right. Combinatorics, that's what I do. Glorified dice throwing. Bloody nerve of you both. You fail on primes and you think you can just turn around and crack partitions. Can't be done, I'm telling you. Especially not by you.
It can. And I will.
So this is a meeting with Major McMahon.
By slow and painful addition, and then you can be absolutely certain that whatever formula you two can dream up will be quite wrong. Then you can crawl back under whatever rock you came from in India, and we can put to bed this charade of yours, Hardy. Now, how high do I have to go?
P of 200 should do. I really can't do it.
So this is a meeting between Hardy and Ramanujan go to meet McMahon. As you can see, they are kind of racist. You can also see kind of somewhat racist overtones in what McMahon was saying, you know, whatever rock you came from in India, you go back to in Chennai. So Ramanujan actually Hardy and Ramanujan had this beautiful formula. That given an integer, like, and this is with 24 colors, any number, he had an analytic formula. So he didn't have to do, you can just put it you can calculate this very quickly. Suppose, imagine I give you 200, and to do it really by hand, as McMahon wanted to do, you would have to work forever. Whereas here, this is a Bessel function. These are some phases, Kloosterman phases. And it turns out that the question of finding how many qubits there are on a black hole for certain kinds of black holes, very similar formulas are needed. So the mathematics of Ramanujan, in this very precise way, in this particular, this is known as the Hardy-Ramanujan-Rademacher expansion. It's an exact expansion, convergent expansion, and which gives you an integer in terms of analytic numbers, integer in terms of complex numbers. So you sum up all these complex numbers and you get an integer. So it's a kind of magical formula. So this is the second meeting of Ramanujan.
100, the moment of truth. You know, I was stationed in Madras once. Yeah. Well, you first. What has your formula given you?
3,972,998 million.
My God. You're close. Within 2%. Well, I'll be damned.
Major McMahon, may I introduce you? Mr. Ramanujan.
Okay. So the point is that the mathematics of Ramanujan somehow became important in understanding the quantum properties of space-time, because And this was, for example, some recent work that we did, that you can actually calculate the exact qubits, number of qubits associated to some black holes. And you can calculate independently using a gravitational calculation. You can calculate from gauge theory, and you can calculate it from string theory. And you get quantized exactly the same. So there is no, you cannot get exactly 512 if you did something wrong using two different ways. So there is something really deeply correct about string theory that we don't yet understand. And somehow there is an integer. The gravity somehow knows about that integer on the horizon. So the quest for the unification of gravity and continues it's with fascinating connections. I mean, quantum black holes, gauge theory and string theory. There are also new connections with quantum entanglement and the structure of space-time. So this is a very exciting area of research, which I will now I will end with this encouragement from Einstein and a warning. So he says that the successful attempt to derive delicate laws of nature along a purely mental path by following a belief in the formal unity of the structure of reality encourages continuation in this speculative direction, the dangers of which everyone who dares to follow it must vividly keep in sight. So it's a good thing to keep in mind that you can be led astray. So you have to have some humility about it. But now what I want to return back to my other theme, and I have maybe 5 more minutes I can take. The unity of science. I mean, you saw, the work of, starting with Einstein, Schwarzschild, Hawking, Ramanujan, people coming from really totally different parts of the world. This is really fundamental to science. This is the unity of science. There are completely unexpected links between quantum black holes, gauge theory, number theory, coming not only from different parts of science, but different parts of the world. And this is where it becomes important to understand why curiosity-driven science and theoretical physics is important sometimes when we talk to policymakers, because it motivates excellence and attracts talent. Young people are excited about the frontiers. It crosses interdisciplinary boundaries. It's easier for theories to cross interdisciplinary boundaries. You can actually make truly disruptive technologies, like, for example, the AI neural networks sort of were started by statistical physicists. The ideas came from a totally different directions. So, of course, you need a healthy balance between pure and applied science and theory and experiment. I'm not saying that. But the advantage of theory is that theory is cheap. So compared to a big experimental facility. So sometimes I joke that ICTP is like a CERN with a blackboard. We don't need a billion-dollar machine. Fundamental science is the driver of technology. And I think when we talk to and which I have been doing, very important to emphasize the essential unity of science for national policies and public investment. Without quantum mechanics, there can be no quantum technologies. So you can be talking about, without basic physics and understanding, as I said, statistical physics and so on, you cannot really do AI. So there is an AI thing going on in Delhi. So overemphasis on technology can be short-sighted. So this is actually a very nice quote of Euclid when Emperor Ptolemy asked him to teach him geometry. After a while, he found it too difficult, and he asked Euclid, can you simplify it? And Euclid is supposed to have said, there is no royal shortcut to geometry. And I would say the same to the Ptolemies of today, that there is no royal shortcut to technology. And the next Ramanujan, how do we create conditions such that the next Ramanujan is not lost? I mean, Ramanujan was almost lost. It is a kind of a miraculous story and a wonderful story. But nevertheless, maybe there is another Ramanujan that we have not encountered. And in this respect, there were two quite distinct visions of Bhabha and Salam. Bhabha wanted to create strong scientific communities in India. Salam went ahead and created International Hub for Science, a very major center. When I became the director, I was sort of trying to understand what should be the vision for ICTP. And having worked both at Tata Institute and ICTP, I came to the conclusion that actually these visions are really should be viewed as being complementary with each other and not in competition with each other. Although in their lifetime, I think Bhabha and Salam didn't quite get along with each other, if I know. So I really believe in the complementarity of these points of views. And this I say actually from my own experience that our ultimate goal would of course be to create a strong and vibrant community in each country. But internationalization remains fundamentally important in science, especially as I've seen, there is this whole diversity of expertise coming from all parts of the world. And we need a global platform. As I said, this other aspect of ICTP's mission of providing an international platform for addressing global challenges. And this is what is the kind of the vision of ICTP for the coming years, that we really need global science for global action. So just to give you an example, cyclones and pandemics do not respect national boundaries or political. The heat wave in Delhi is not going to stop in Delhi. Now, you need to have a platform where the climate science of this region is discussed. So any viable action, especially in climate, which is an existential problem for humanity, must involve the countries which are affected, global south, in equal partnerships. Otherwise, you are most likely to land up with a very technocratic solution, which really does not take into account the interests of those who are affected. And how do we do that? We need to create scientific communities who can deal with this knowledge. And for example, ICTP has been organizing monsoon workshops, and this is the recent agreement that we are trying to sign with the Ministry of Environment, that another climate workshops at ICTP, funded by the Ministry of Environment. But the advantage is that we being a UN organization, Pakistani and Chinese and Indian climate scientists can come together and talk to each other in peace without worrying about the political or visa regimes. So this is what I have called International Science Alliance. And we have been successful in getting agreements with several major universities and national agencies, also corporations like IBM and Quantinuum in major supercomputing facilities in Italy and Switzerland, major foundations like Simon's Foundation and Arab Fund, and also various countries, South Africa, Brazil, Kuwait, India, China. So I will end here. We also have another initiative called the International Consortium for Scientific Computing, which is kind of related to this. But the vision of ICTP for the future, and I think this is a good point to end, that Salam had a certain ideas in the 60s, and we of course cannot keep on parroting the same logic. Or similarly, Bhabha and his generation had certain goals. I think it's fair to say that the goals that they had set for themselves have been met, I would say. I think for the coming years, for the next generation, one has to think anew. What should be the priorities? What are the national priorities? What are the areas you want to emphasize? And likewise at ICTP, we cannot continue with this same kind of modalities that Salam had. The inspiration remains the same, but the implementation has to be thought anew. And this has been my effort over the last few years. And I envision really ICTP in the coming future years as a kind of a lighthouse for global science. This is actually Faro della Vittoria. It's like the Victory Lighthouse in Trieste. You can see the ICTP is here in the background. And I think this is a very nice kind of symbol for ICTP. I hope that it continues to be a lighthouse for science. Thank you.
Thanks very much, Atish, for unifying all these different aspects. And before we take questions, as a small memento, a sweatshirt and a mug for ICTS as a keepsake. So thanks very much. And I'm sure Atish will be happy to take questions. Please raise your hand and someone will come to you with a mic. Yeah, Oscar.
Thank you for your beautiful lecture on unification, unity, collaboration, crossing borders, and anniversaries. And I want to tell a story that is also about unity and anniversary. Is more modest, but is, I think, very relevant for the program that is currently going on here. And you mentioned people like Yang, and you mentioned Simons, and after efforts that they did together 50 years ago, actually last December, there was a paper, an article by Yang and Wu, where I think the subject I don't remember, but the significance is that there was a dictionary that related the terms of gauge theory to geometry, to differential geometry.
term
And
class.
that has been tremendously influential in bringing the two communities of theoretical physicists and mathematicians together. And I must say that what is happening in our current program is very much a product of that. So I just wanted to comment on that. Thank you.
Yeah.
That's very appropriate. Yeah, indeed.
It's like the
title
monopole
of
charge. Yeah. Monopole charge being
monopole and
Chon
the
class.
whole vector bundles, the whole dictionary connections, parallel transport. Yeah, and in fact, this a major theme here are Higgs bundles, which in some sense is very is inspired from the original works. So yeah, other questions?
Good evening, sir. So, firstly, I wanted to comment and congratulate you on your industry and political efforts and viewpoints. Now, where my questions arises, I was actually waiting for you to step into gravity because electronuclear forces are kind of foundational and even primitive to understand quantum mechanically and classically. So, when you come to gravity, what I was actually wondering is it's kind of ruggedy to frame, but in the sense that gravity is something that is extremely different from our three fundamental forces. So, and when you describe a force, it goes into a waypoint, into a viewpoint that it's just an effect of displacement primarily. So, how would we regard gravitation as a force as a whole, looking at its diversions from fundamental forces, and why not for it to be just an effect of um, displacement in space-time, right? Because that is what Einstein's theory primarily describes it as. And then, of course, we try to quantum mechanically describe it using gravitons and all of that. But even gravitons are extremely theoretical to a point that they are hypothetical as of right now. And also, another question that arises from that is when you try to look at it through a theoretical framework, how would you correspond it with data? As you know, you were explaining it through Hawking's theory. How would you kind of equate it with qubits when you actually don't have any data of a black hole at all?
Yeah, so gravitational waves have been discovered experimentally now. So there is no question that gravity travels in waves. Now, it is well known, actually, there is a famous paper of Heisenberg that you cannot have a disturbance, classical, you cannot have a theory in which part of the theory is classical and part of the theory is quantum. So if electromagnetic waves are quantized and have photons, it is essential that you quantize also gravity. If you don't do that, for example, you can construct a Heisenberg microscope and you can violate the uncertainty principle in other parts of the theory. So for the coherence of the theory, it's necessary that everything has to be quantized. So therefore, gravitons, if gravitational waves exist, gravitons must exist. They may not be detectable in the same way that we can detect photons. Regarding the Hawking's work, as I said, it is really impossible that any time in the future, the formulas of Hawking radiation will be verified experimentally because the temperatures are very low. But no serious theoretical physicist doubts that Hawking's calculation is fundamentally correct and very beautiful, because the reason for being it is that it's a little bit like the 19th century physicists who didn't know about quanta, but they knew about thermodynamics. So thermodynamics was a very powerful guide, and statistical mechanics. I mean, Boltzmann made this great leap, because of which, knowing thermodynamics and thermal properties, some of the more far-seeing physicists of the time, like, for example, people had discovered, like, I think it was Gibbs had understood that there is something wrong with the specific heat of solids, because it was not, and it required quantization. Sorry, Gibbs discovered this n factorial. He discovered that identical particles, the statistics has to be identical. So he put in a factor of n factorial by hand. It took 50 years before the n factorial was actually understood as a consequence of the spin statistics theorem in quantum field theory. So sometimes the progress can be made. It is more difficult, as Einstein's warning shows, that we would all love, all of us, including myself, if tomorrow there was an experiment in the lab which would verify, or Hawking would have loved it, if the Hawking radiation could be verified. So that is not the situation we are in. But the calculation itself is based on such solid principles that no one really doubts it, because it's based on solid foundational principles like thermodynamics, quantum mechanics, things that we understand very well. So that is the way we are making progress in this admittedly difficult field where experiment is not guiding us.
Just another add-on.
Maybe we'll just take some more questions, and then if there's time, we'll come back. I think Smriti had a question there. Yeah, we'll come back there.
This was more about the policy. You said that at the end, you would say something about equal partnerships with institutes in India and so on. Can you elaborate a little more on that?
So this is what I've called the International Science Alliance. So in Salam's times, for example, we had hundreds of agreements with many different universities, but usually they did not really translate into anything substantial. Because let's say you had an agreement with University of Lahore or with Bombay, or University of Bombay, or there were no new additional funding was made available. Now, currently in India, the situation, or in China, or in Brazil, where we have now beginning to sign agreements, the point is that both intellectual and financial resources are not lacking. I mean, the financial resources are not lacking. There is also very strong local communities. So it is not at all the situation like it was in the 60s. I mean, I would say that even that the model in the 60s was a bit patronizing in a way. It was one directional. Now it is not the case that, I mean, we have, I mean, ICTS exists, Tata Institute exists, really wonderful places exist in China, in Brazil. So question is, even for those institutions, and this is my experience, that it is really very important for the internationalization. I was in Brazil, or also many Chinese universities. They're very keen to have this opportunity of internationalization. But then the idea would be that, can we get funding from the Brazilian government or from Chinese universities, which we will target not for doing something else at ICTP, but for the community there, because of which we can do more. I mean, we get, as you know, the spring school in string theory, we get, 500 applications, and we select 150. If we have additional funding from Indian government or DST, we can, instead of selecting 5, we can select 15. So, which is relatively easy for us to do. So it's a kind of a mutually beneficial arrangement. So that's the kind of model that I would like to move to at a more national level. And I think we have been modestly successful so far. In this direction, we have had some success. And of course, private funding, where we have had much bigger success. But we need both these new resources to come in to really enhance the mission of ICTP.
Just to follow up, I mean, the joint activities is a think that would be one way to do
Yes,
have
which we have
equal,
been,
like
which we have been
we
doing with
have been doing with
ICTS, is that
ICTS.
we alternate the activities between ICTP and India, so that the Indian community don't have to all travel to. But every 2 years they have an opportunity to go there, maybe, or every 3 years, and interact with the broader community, which may be sometimes difficult to bring them here. So I think there are advantages. So this is certainly a model that worth following.
And in fact, during the ICTP, ICTS joint schools on quantitative biology, we got additional external funding to bring people from other developing nations to India. So a lot of people from Brazil, Africa, Southeast Asia, and all came. It was very good in that sense. Some interference between our mics. So I think it's a.
Yeah, I think that's really causing. Yes, no problem.
Yeah. In any case, I wanted to just say that it was one way in which even internationalizing Indian science also happened.
I think
that way.
we would like to work in both directions, not only international. I mean, so, but again, as we see, the model is very different from in the 60s.
Actually, I think you sort of answered my question. I was just going to ask, you made a comment that Abdus Salam's original vision maybe needed updating, that the world had changed since then, and I was going to ask you to elaborate a little bit on that, but that's sort of what you...
Yes, but as you can see, the geopolitics is very different. I mean, in Salam's time, the issue was the Cold War, and there was an Iron Curtain. So actually one of the first plasma physics conferences took place in 1964 at ICTP, where the Soviet plasma physicists could meet American plasma physicists for the first time outside in a neutral territory. Now today, the challenges are different, and AI, climate research are actually very important, perhaps as even more threatening than nuclear. Unfortunately, that threat has not gone away. So we have added 2 more threats to our existence. And it's, I think, fundamentally important that there exists a place like ICTP where some kind of a dialogue is possible, some kind of a discussion is possible, even for international kind of negotiation to happen. And I think that is a very important role that's going to become more and more important, especially with all the kind of apprehensions people have about AI and quantum and securing national security and closing the boundaries and not allowing people to travel. ICTP could remain the kind of the oasis where people can still come together without worrying about these political implications.
Hi. Yeah, so after the inception of ICTP, of course, we have this ICTP cipher in Brazil and also ICTP AP. Are there any such plans for having more such centers? Because as you're mentioning, sometimes it's tough to travel all the way. Like from here to Brazil, it's quite a long journey.
So this is what we have called the partner institutes. And I would look at it as an experiment. And the experiment has been very successful in Brazil and has not been so successful in other. But I think India would be a very natural destination for such a partner institute. But it requires a lot more planning and thinking. It's not something that one can just, again, you can sign agreements and have photo ops, and it's like a friendship deal. But if you really want to put it in practice and really do something on the ground, it requires very detailed thinking. And if that is not done, then it will not succeed. You can just get some empty shell. But I think it's in Indian context, it actually makes a lot of sense to have ICTP. ICTS is already such an example. So our centers are UNESCO's category 2 centers. We are UNESCO category 1 center. UNESCO category 2 means that they are more or less governed by the national laws and they don't become UN entities specifically. So it keeps them separate from, gives them the freedom to do the things in the national framework. But they can have some additional benefits of being connected to a UN entity. This is something worth considering. I mean, my meetings in Delhi with the DST are sort of a beginning step in that direction. But as I would say, this requires a 5-year planning. It's not something that can be done in 2 years.
So just to follow up, does this amount into creating more centers or like converting an already existing center into like institute into a ICTP center? Because the Sao Paulo one is more of the second kind, I imagine. I'm not sure.
No, I think it was really created as a
Completely
from
independent
scratch, yeah.
entity.
So, the last question.
Your lecture reminds me of last year's lecture by David Gross, Nobel Prize, 2010 Nobel laureate. He was similar lines. I have enormous questions, but I believe in quantum entanglement. I live in quantum entanglement. I believe that I will get answers from my own instinct. If I want an answer from Einstein, I will get it because his intellect is alive. For Ramanujan, if I want, I can take it from. I just want to compliment your lecture. It inspires me and it inspires a lot of questions. I'll have the answers myself.
Yeah, thank you. I should actually acknowledge a couple of the slides. Actually, I gave this talk, a similar talk, together with David Gross in California recently. So with his permission, I stole a couple of the slides. So you don't be surprised if you found a couple of the slides very similar.
It's entanglement. Okay, so let's conclude there, and let's thank Atish again for an inspiring talk.